Power transmission products. They're everywhere. But when it's your job to select the right product for the right application, it's important to understand a few engineering principles to make the right choice. To help you, this video will review the basics of power transmission. First, let's examine the systems used to calculate and measure power transmission. Engineering calculations of things like weight, force, length, and time are made with two widely used systems. The British Engineering Unit, abbreviated BEU, is the system of choice in countries following American engineering methods. Outside of English influence, the remainder of the world uses the International Standard System. Engineers use these systems to measure motion, both linear and rotary, plus loads on components like gears and bearings, the amount of friction or resistance to movement between components, and much more. When engineers know the answers to such things, they know what to specify in any power transmission system they build. Let's look first at the simplest form of power transmission: linear motion. Linear motion is produced by a physical object that is moving in a straight line. For example, this section of a conveyor. Suppose you need to move a box 50 feet in 10 seconds on a conveyor. How fast must it run? To answer, you need to divide the distance by the time taken to travel that distance, which will give you the conveyor's velocity. In this case, 50 feet divided by 10 seconds gives a conveyor velocity of 5 feet per second. Using similar formulas, engineers can calculate the acceleration or deceleration of an object by computing the velocity and the time of travel, which is important in determining when some power transmission products reach their peak performance, or the mass of an object, once they know its weight and how fast gravity accelerates it, which is important in determining how much power needs to be transmitted, or the force needed to move the mass of an object and accelerate it to a given velocity, which is critical in determining how much power transmission can be allowed to fluctuate. In the case of rotary motion, where an object is spinning around an axis, different fundamentals would seem to apply. Actually, however, the same principles apply to rotary motion. Straight-ahead velocity in linear motion becomes angular or rotational velocity in rotary motion. Linear force becomes the rotational force known as torque, and so on. In the case of power transmission, it's more important to study rotary motion than linear motion, because almost everything that drives a power transmission system is a rotating prime mover. For example, an electric motor or the drive shaft of an internal combustion engine. Refer to the handbook for methods of measuring the velocity of rotary motion versus linear motion. Those methods would seem to be different than linear motion because linear is in a straight line, while rotary velocity is taken off an object that revolves. Actually, however, it's only the number of the measurement that's different. Each method of measurement is the same for either linear or rotary motion. That is, measuring the distance traveled at a certain speed. This distinction is important because the rotary motion itself is not going anywhere. It's sitting there, spinning. What it's moving is what should be measured. For example, a 1-inch drive wheel travels 3,140 inches per minute at 1,000 RPM. A 2-inch drive wheel travels the same distance at 500 RPM. So the speed of travel is different from the speed of rotation, something every power specialist must keep in mind. In addition to the velocity of rotation, engineers must determine how effectively the rotary motion causes movement, how much potential the motion has for doing work. This effectiveness, this potential, is in effect called torque, which is simply the tendency of the rotary motion to twist whatever it acts upon. Normally, a driven shaft Generally speaking, systems today do work with lower torque and higher speeds. But there are exceptions. That's why torque measurement is important when designing the system. Engineers measure torque in foot-pounds, that is, how far away from the axis of rotation, in feet, the twisting effect of torque in pounds is applied. So an engineer who wants to exert 50 pounds of torque in 1 foot, and another who wants 25 pounds of torque in 2 feet, may need the same power unit. Another important principle of power transmission by rotary motion is inertia. Simply put, inertia is the tendency for an object that isn't moving to remain that way. Or, more significantly for power transmission, the tendency to keep moving in the same direction unless acted upon by some outside force. In other words, if the power were cut off, but this component were rotating in an environment unaffected by friction or gravity, it would continue to rotate. But there is no such environment. Friction or gravity will eventually overcome rotational inertia, but it will stop a small rotating component before it will stop a large one, even if both weigh the same. That's because inertia multiplies upon itself in power as the component gets larger. So once the component is rotating, it doesn't need nearly as much power to keep it rotating. Inertia will. And that's a crucial element in an engineer's calculation of power transmission needs. Another crucial factor involving both torque and inertia is using a speed changer to increase or decrease the power transmitted by the prime mover. It's crucial because changing the speed can improve or degrade the performance, that is, the torque and inertia of the entire power transmission system. For example, this reducer lowers the speed by a factor of 5, but it lowers the inertia by a factor equivalent to itself, 5 times 5, or 25 times less inertia. And a speed increaser does exactly the opposite, 5 times 5, or 25 times more inertia. The effect on torque, however, is the opposite, though not as greatly. The same reducer that decreases speed by 5 times increases torque by 5 times. And the same 5-to-1 speed increaser decreases torque by 5 times. Torque and inertia, when under the influence of a speed changer, a relationship of opposites.